If we do not know the number of elements subject to a certain risk, but instead have information about the average number of events that occur per unit of time, we could use a Poisson distribution to count the number of elements that could probabilistically occur. A Poisson distribution only requires one parameter, the mean frequency of occurrence. Place your cursor in cell B13. Notice its syntax. Equals if error, dt Poisson, B12. At its heart, it is a Poisson distribution that models the number of annual for customers, products and business practices events for the credit management unit, with an average of 3.22 events per year. Note that this number does not necessarily have to be an integer, since it is simply the calculation of an annual average as we see it calculated in the previous cell B12. A Poisson distribution always returns only integer values, with a mean and variance equal to its only lambda parameter, 3.22 in this case. It is generally used to describe, for example, the number of individual events that occur in a time interval when events occur at a constant rate, the number of customers arriving in a queue, the number of accidents on a highway or the number of imperfections per meter of an item being manufactured, the number of items in a batch of random size, the number of items required from an inventory, the number of periods, months, days, that a device is out of service or the number of claims on an insurance policy. In this case, we are using it to stochastically count the number of annual events from customers, products and business practices for the credit management unit during the previous 5 years. This distribution describes how eventual random numbers will be generated during a simulation. When looking at the height on the y-axis of each bar, the probabilities are considered. Since the annual average of events is 3.22, there is only about a 4% probability that there are no events. On the other hand, there is a 13% probability that exactly one event will occur per year, given that lambda, the annual mean, is 3.22. The number of events that would occur most frequently is 3. In approximately 22% of cases, this Poisson would generate 3. Exactly 8 events per year would occur in only 1% of cases. Click F9 to recalculate your randomly generated Poissons multiple times and notice how the values in cell B13 now change each time you recalculate. This is a test of the random number generator engine that DT Simulator has that is generating random numbers when new Excel calculations occur, based on the Poisson distribution and its corresponding lambda parameter equal to 3.22. Also, consider that certain discrete distributions can be adequately represented by continuous distributions. For example, if we select all units now, lambda becomes a much larger number of almost 54 events per year. Notice what the Poisson curve generated here would look like. See how the possibilities of frequency of events around such an average begin to densify. By selecting all risk categories with a mean of almost 224 annual events, the respective Poisson has been densified many times, generating numbers that will oscillate around their mean in a distribution that has been normalized. In fact, the normal distribution, by virtue of the central limit theorem, being the sum of independent random events, is the curve to which a Poisson would naturally converge as we increase the average number of elements that compose it.